We all wonder how things end. A book, a movie, a life. It's a human thing to do. So, it's natural to ask the biggest question of all. How does the whole show, the entire universe, finally close? There isn't one simple answer. Nobody knows for sure. What we have are ideas, theories. These are stories about the future, based on the clues the universe gives us today. And the biggest clues are about how the universe is behaving right now. It started with the Big Bang. That wasn't an explosion in space. It was the beginning of space itself, and time, and everything in it. Since that first moment, the universe has been expanding. We know this because we can see it happening. Distant galaxies are moving away from us. And the farther away they are, the faster they're moving. For a long time, scientists thought this was a simple story. The universe got a big push at the beginning. Now it's coasting. Gravity, the force that pulls everything together, is acting like a brake. So there were two main possibilities. Either there was enough stuff, enough matter, and gravity to eventually stop the expansion and pull everything back together. Or there wasn't, and the universe would expand forever, but slower and slower over time. It was a cosmic tug of war between the outward push of the Big Bang and the inward pull of gravity. Then, in the late 1990s, we found something new. Something strange. The expansion isn't slowing down. It's speeding up. This was a shock. It was like throwing a ball into the air and watching it fly faster and faster into the sky instead of falling back down. Something was pushing everything apart. Something was working against gravity. We don't know what it is, so we give it a simple, honest name. The dark energy. This dark energy seems to be a property of space itself. The more space there is, the more dark energy there is. And since the universe is expanding, more space is being created, which means more dark energy is being created. Which means the expansion speeds up even more. It's a feedback loop. This discovery changed everything. It rewrote the possible endings to our universe. The old story of a simple tug of war was wrong. There's a third player in the game, and it seems to be winning. Most of the theories about the end of the universe are now stories about dark energy. The most likely ending, based on what we see today, is probably the least dramatic. It's called the Big Freeze, or the Heat Death. It's a long, slow, quiet end. The story of the Big Freeze starts with the acceleration we see now. As space expands faster and faster, galaxies will continue to move away from each other. At first, this doesn't change much. For a few billion years, our local neighborhood will be fine. Our own galaxy, the Milky Way, is on a collision course with our nearest big neighbor, the Andromeda Galaxy. They will merge in about 4 or 5 billion years to form a new giant galaxy. But outside our local group of galaxies, things will start to look empty. Over billions, then hundreds of billions of years, the accelerating expansion will carry all the other galaxies away from us. They will move away so fast that their light will no longer be able to reach us. They will cross a cosmic horizon, a point of no return. One by one, the galaxies will wink out of our sky. The universe beyond our own newly formed supergalaxy will become invisible. It will still be there, but it will be forever out of reach. The sky will become black and empty. Inside our own galaxy, things will continue for a while. Stars will keep burning, new stars will be born from clouds of gas and dust, but this can't last forever. The gas runs out. Star formation is a finite process. The era we live in now, with bright stars lighting up the night, is called the Stelliferous Era. The era of stars, it's the youth of the universe. But it will end. After a few trillion years, the gas needed to make new stars will be used up. The process will grind to a halt. No new stars will be born. The existing stars will start to die. Stars, like our sun, will swell up into red giants and then shrink into small, dense, white dwarfs. Bigger stars will have already exploded as supernovas, leaving behind neutron stars or black holes. The last stars to go will be the smallest ones, the red dwarfs. They sip their fuel so slowly they can last for trillions of years. But eventually, they too will flicker out, becoming cold, dead embers. About 100 trillion years from now, the last star will die. The universe will go dark. The Stelliferous Era will be over. What's left is a graveyard. A universe filled with the corpses of stars, white dwarfs, neutron stars, and black holes, all floating in a cold, dark void. Planets will still orbit these dead stars frozen solid. This is the beginning of the degenerate era. The universe will be a quiet place, but not completely dead. Things still happen, just on timescales that are hard to comprehend. Galaxies themselves will start to fall apart. Over quadrillions of years, the gravitational pull between the dead stars isn't strong enough to hold them together forever. Random encounters will fling some stars out into the intergalactic darkness. The rest will slowly spiral into the supermassive black hole at the center of the galaxy. And there's another, even stranger process that might happen. We think that protons, one of the basic building blocks of matter, might not be stable forever. Some theories suggest they can decay. It takes an incredibly long time. The estimated half-life of a proton is more than a trillion times the current age of the universe. But in the endless time of the degenerate era, that's no problem. If protons decay, then all the dead stars and frozen planets will slowly evaporate. A white dwarf isn't really a solid object. It's a degenerate gas of atomic nuclei and electrons. If its protons and neutrons decay, it will slowly dissolve into a puff of radiation and light particles. This process is unbelievably slow. A diamond the size of the Earth would take longer than you can imagine to dissolve. A whole dead star would take even longer, but time is all the universe has. Eventually, all matter as we know it would be gone. After the last proton decays, the only things left in the universe will be black holes, and a thin soup of basic particles like photons and neutrinos spread far apart. This is the black hole era. For a long time, we thought black holes were the ultimate prisons. Nothing could escape. But Stephen Hawking showed that's not quite true. Black holes can evaporate. It's a process called Hawking radiation. They slowly leak energy back into the universe. It's a trickle, not a flood. A black hole the mass of our sun would take an absurdly long time to evaporate. A supermassive black hole from the center of a galaxy would take even longer. We're talking about numbers so big they don't have names. A1 followed by 100 zeros of years. This number is called a googol. The time for a big black hole to evaporate is a googol times a googol times a googol. But it will happen one by one. Even the biggest black holes will shrink. In their final moments, they will erupt in a flash of light, their remaining mass converted into energy. And then they will be gone. After the last black hole evaporates, that's it. That's the end of the line. This is the dark era. The universe will be nearly empty. It will be a cold, thin, uniform soup of photons, neutrinos, and other fundamental particles, all spread impossibly far apart. The expansion will have stretched space so much that these particles will almost never interact. The universe will have reached a state of maximum entropy. Entropy is just a technical word for disorder or sameness. It's the universe's tendency to get messier and more spread out over time. A hot cup of coffee cools down because its heat spreads into the room. It never happens the other way around. The universe will have reached room temperature. Everywhere. There will be no hot spots, no cold spots, no structures, no way to get any useful work done. All the energy will be dissipated. This is the heat death. Not a hot death, but a cold one. A universe where the temperature is just a tiny fraction of a degree above absolute zero everywhere. Nothing happens. Nothing will ever happen again. Time itself might lose its meaning. It is the ultimate, final, permanent end. That's the most likely scenario. It's a bleak picture. A long, slow fade to black. But it's not the only possibility. Our understanding of dark energy is very incomplete. What if it behaves differently than we expect? This leads to a more violent ending. The Big Rip. The Big Freeze assumes that dark energy is a constant, a property of space that stays the same over time. But what if it gets stronger? What if the amount of dark energy in a given volume of space increases as time goes on? Scientists call this idea phantom energy. If this is true, the feedback loop gets out of control. More space means more dark energy, which makes space expand faster, which means even more space and even stronger dark energy. The acceleration itself accelerates, and this leads to a terrifying conclusion. In the Big Freeze, structures like galaxies stay bound together by their own gravity for a long time. The expansion happens in the space between galaxies, but in a Big Rip scenario, the push of phantom energy eventually becomes strong enough to overcome everything. Even gravity. The timeline for the Big Rip is much faster and more dramatic. It would start similarly, with distant galaxies disappearing from view. But then the ripping would begin. The phantom energy would become so strong that it would overcome the gravity holding galaxies together. The Milky Way would be torn apart, stars would be flung into the expanding darkness. But it wouldn't stop there. As the expansion continued to accelerate, the dark energy would become strong enough to overcome the gravity holding individual solar systems together. The Earth would be torn away from the sun. The planets would fly off on their own. The end would come quickly after that. A few months before the final moment, the Earth itself would not be able to hold together. The force of the phantom energy would be stronger than the gravity binding our planet. The Earth would explode. A few minutes before the end, the sun would be torn apart. In the final seconds, the force would become stronger than the electromagnetic forces holding molecules together. Everything would be broken down to individual atoms, but it wouldn't even stop there. In the last fraction of a second, the phantom energy would become stronger than the strong nuclear force, the force that holds atoms themselves together. Atomic nuclei would be ripped apart into protons and neutrons, and then, at the very last instant, those particles themselves would be torn apart. Space-time itself would be ripped. The end would be a rip singularity, where the expansion rate becomes infinite. Every single thing in the universe would be shredded into its most fundamental, unbound components. The universe would cease to exist in any meaningful way. The Big Rip is a spectacular and terrifying idea. And whether it could happen depends on the true nature of dark energy, which we just don't know. Our current measurements suggest dark energy is constant, which points to the freeze. But the measurements aren't precise enough to rule out the rip completely. Of course, there is another option. The old favorite, the Big Crunch. Before we knew about dark energy, this was a leading candidate for the end. It's the simplest story. The Big Bang pushes everything out. Gravity pulls everything back in. If there is enough matter in the universe, enough gravity, then one day the expansion will slow to a halt, and then it will reverse. This would be the Big Bang in reverse. Instead of galaxies flying apart, they would start rushing towards each other. The universe would begin to shrink. At first, this would be slow, but as the universe got smaller, galaxies would get closer together. They would start to collide and merge. The universe would become a crowded, chaotic place. As the universe continued to shrink, the temperature would start to rise. The background radiation that is currently just a few degrees above absolute zero would heat up. First to room temperature, then to the temperature of a star's surface. The sky would glow with a blinding light. Stars would begin to be torn apart by tidal forces and the intense radiation. The universe would become a hot, dense plasma, like the inside of a star. As the crunch neared its final moments, the temperature and density would become unimaginable. Atomic nuclei would be broken apart. The four fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, might merge back into a single superforce. Finally, everything in the universe, all matter, energy, space, and time, would collapse back into an infinitely hot, infinitely dense singularity. The same kind of point from which the universe began. The Big Crunch seems unlikely now. The discovery of accelerating expansion, of dark energy, suggests there's not nearly enough gravity to stop the expansion, let alone reverse it. The universe appears to be underweight for a crunch, but again, we don't know for sure. If dark energy were to weaken, or even switch from a pushing force to a pulling force in the distant future, a crunch could still be on the table. The Big Crunch also has an appealing follow-up, the Big Bounce. What happens at the singularity of a big crunch? Does everything just end? Or could that immense pressure and energy trigger another Big Bang? This is the idea of a cyclical universe. A universe that is born, expands, collapses, and is born again. Our Big Bang might not have been the first. It could have been the result of a previous universe collapsing. The Big Crunch leads to a Big Bounce, which leads to a new Big Bang and a new expanding universe. Over and over, forever. This idea solves the problem of the beginning. The universe didn't have a beginning. It has always existed in a cycle of birth and death. It has a certain philosophical beauty to it, a cosmic rhythm of inhalation and exhalation. But it relies on physics we don't understand. Our current theories, like general relativity, break down to the singularity. We don't know what happens there. So the Big Bounce remains a fascinating but highly speculative idea. There's one more scenario to consider. It's different from the others. It's not about the long, slow evolution of the cosmos. It's about a sudden, catastrophic change. It's called vacuum decay, or the false vacuum. This idea comes from particle physics. It suggests that the vacuum of space might not be in its most stable state. Think of it like a ball resting in a small dip on the side of a large hill. Stable for now. But it's in a false vacuum. The true vacuum, the state of lowest possible energy, is at the bottom of the hill. If the ball gets a big enough nudge, it could roll over the edge and fall all the way down to the true bottom. In the quantum world, such a nudge can happen randomly, without any cause. The theory of vacuum decay says our universe might be in one of these false vacuums. If somewhere in the universe a tiny patch of space randomly tunnels through to the true vacuum state, it would create a bubble. Inside this bubble, the rules of physics would be different. The properties of fundamental particles, like electrons and quarks, might change. The forces that govern them might be different. The very nature of reality would be rewritten. This bubble of true vacuum would expand outwards in all directions at the speed of light. And as it expanded, it would convert the false vacuum of our universe into the true vacuum. It would be the ultimate death machine. We would never see it coming because it travels at the speed of light. No information can warn us. One moment, everything is normal. The next, the bubble wall arrives, and you, the Earth, the solar system, the galaxy, are instantly obliterated and replaced by a region of space with different laws of physics. It's not death in the normal sense, it's erasure, the end of existence itself. Is this likely? We don't know. To figure it out, we need to know the precise properties of particles like the Higgs boson and the top quark. Our current measurements suggest the universe's vacuum is stable, or at least metastable, meaning it will last for an incredibly long time. It probably won't decay for trillions of years, if ever, but a small change in those measurements could change the forecast. Vacuum decay is the ultimate wildcard, a sudden, silent, and final end. So where does that leave us? We have a collection of stories about the end. The Big Freeze is the current scientific consensus. The long, slow fade into cold darkness. The Big Rip is its violent, angry cousin. The Big Crunch is the old, symmetric story of a return to the beginning, which might lead to a big bounce. And vacuum decay is the sudden shock, the quantum accident that ends everything without warning. The truth is, we are standing on a tiny rock in a brief moment of cosmic time, looking out at an enormous, mysterious universe. We only understand about 5% of what it's made of. The rest is dark matter and the even more mysterious dark energy. The ultimate fate of the universe depends on the nature of that darkness. Will dark energy remain constant, leading to the freeze? Will it grow stronger, leading to the rip? Will it weaken or reverse, leading to the crunch? Or is there a fundamental instability in space itself that will one day give way? We don't have the answers. Not yet. Maybe that's okay. The timescales we are talking about are beyond human comprehension. Trillions upon trillions of years. The end of the universe is not a problem for us. It's not a problem for our children or for humanity or for the Earth. The sun will burn out long before any of these cosmic endings come to pass. The real story here isn't about the end. It's about the fact that we can even ask the question. We are a part of the universe that has become aware of itself. We can look back at the beginning and forward to the potential endings. We can use science to tell these epic stories. It's a strange and wonderful position to be in. To live in the Silliferous Era, a brief, shining moment when the universe is filled with light and life and wonder. The end will come, in one form or another. But for now, the show is on. And we have a front row seat.